This video is about computations with accuracy and precision, and you may hear my kids in the background. So imagine that you are asked to measure a store's flat asphalt parking lot and hilly rough ground right next to it. How would you measure the parking lot? How would you measure the hilly ground? And after you have the two measurements, how confident are you in the precision and accuracy of the result when you add it together? So for the parking lot, since it's flat and even, you can measure it pretty accurately, maybe using a metal tape, a metal measurer. So you can achieve a high degree of precision. Let's say you measure it to be, I don't know, not the next slide, 27.8 feet. Meanwhile, the hilly ground, you don't have great tools. Perhaps you could use surveying instruments, but let's not go there. Let's just say that you end up pacing it off. You end up with a really approximate answer. You end up with maybe 32 feet. I'm going to change this first one. Let's say it's 25.85 feet. We could probably get to the nearest hundredth of a foot. So if we add these two numbers together, on the surface, it looks like this. It looks like you end up with 57.85 feet for the combined measurement. But the thing is, do you really want to turn into your boss that this is accurate to the nearest hundredth of a foot? The Achilles heel here is that this hilly measurement is only accurate to the nearest foot. And so what it turns out is we can only have our answer accurate to the nearest foot. You would go back and tell your boss that it's about 58 feet. You can't rest on this level of detail because we just don't have that level of accuracy with this second measurement. So to add and subtract measurements, make sure that you have the same unit. So if one measurement is in centimeters and another's in meters, you better do some unit conversion first. Do the operation and then round to the same level of precision as the least precise number. And it just occurred to me that I was referring to the first measurements as accurate. It should be precise. Should have been talking about precision. So what we're looking at is we're looking for the roughest measurement, the one that's the most imprecise. So for example, if we were adding these four measurements together, I first noticed that they're all in grams, and then we can just take out our handy dandy calculator and add them all up, and we get 2,186.34 grams. But now we need to round. And for rounding this, I'm looking for the roughest or least precise number, so the one that's the most imprecise. 407 is precise to the nearest 1 gram. The next number is precise to the nearest tenth of a gram, which means it's more precise. We don't want to use that one. The third one is precise to the nearest hundredth of a gram. And the last one is again precise to the nearest tenth of a gram. The most imprecise, the roughest rounded number is this first one, where it's rounded to the nearest 1. So that means we want to round this answer to that same level of precision or imprecision. 2,186 grams is the answer. We cannot get more precise than that. Let's do another one. I encourage you to pause the video and try this one for yourself. A welder weighs some bins of scrap metal in different scales. The bins weighed 266 pounds, 620, and 1,200 pounds. If we add all of that together, we would add it to be 2,086 pounds. Now we need to round. So for rounding, again, we're going with the least precise, so the most imprecise. So this is 266 pounds is rounded to the nearest 1 pound. And I know that because the last significant digit is in the ones column, the ones place. 620 pounds, remember that last zero is not significant, so this is significant to the nearest 10 pounds, precise to the nearest 10 pounds. The third one is actually the most imprecise. Those last two zeros are not significant, which means this is precise only to the nearest 100 pounds. So that means our error could be plus or minus 50 pounds on either side of that. Since this is the most imprecise measurement, we need to round our answer to the nearest 100 pounds. Round to nearest 100 pounds. So there's our hundredths place. Since the number afterwards is more than halfway, so it's 5 or more, that means we round up to 2,100 pounds. That's our answer, not 2086. That was for addition and subtraction. These next slides have to do with multiplication and division. When we add and subtract what we just did, we track the precision of the numbers. When we're multiplying and dividing, instead, we track the accuracy. So here, units matter a lot less. You want to just do your operations and round the result to the same number of significant digits as the least significant figure. So if something has 3 significant digits and 2 significant digits, you want to round your answer to the one that only has 2 significant digits. So, for example, let's multiply 4.7 ohms by 0.0281 amps. So that horseshoe-like symbol, it's Greek omega, and it stands for ohms. So if we multiply these two, whoops, I gave the answer. If we multiply these two numbers together, that equals 0.13207 ohm amps. So you just smash the units together. However, this is not our final answer because it's probably the wrong accuracy. So for accuracy, I'm going to look at the accuracy of 4.7. I see it has 2 significant digits, and 0.0281, which has 3 significant digits. We want, because those lead zeros are not significant, we want the least significant number, which means we need to round our answer to just 2 significant figures. The 1 is significant, the 3 is significant, so we want to round to the nearest hundredth of an ohm amp. Our answer is 0.13 ohm amps because the following number, the 2, is not halfway, meaning it's less than 5, so we round down. Last problem, 0.497 newtons divided by 1.4 meters times 8.0 meters. So before I even do the computations, we can look at the number of significant figures for each of these. The numerator has a significance of 3, 1.4 has a significance of 2, and 8.0, that last zero is considered significant, so it also has a significant number of significant digits of 2. So our answer, I know we're going to round to 2 significant figures. If we do the computation, that works out to be 0.044375, and then the units, we have newtons on top, that's the capital N, and then we have meters times meters in the denominator, which means that's going to be meters squared in the denominator. This is not our final answer because it's not rounded. So we want to round to just 2 significant figures. So our first significant figure is that first 4, and the next one is the second 4. We look to the digit afterwards. Since it's 3, we round down, and our answer is 0.044 newtons per meter squared. Thank you.